Swayam Prabha. Digital India. Educated India.
Good morning, student. Welcome to the NPTEL course on architectural acoustics. Today we will going to start the 6th week program of the total 8-week module. The lecture number 26 today will deal with the electroacoustics, and I have 2 lectures for that. The lecture 27 is also on the electroacoustics. So, let us first go to the learning objective of this 26th lecture. The electroacoustics is one of the integral part of the acoustics and modern days acoustics, I must say. And the electroacoustical component, it has actually various components, and from the various components there are various fundamentals and some properties of those components. In the lecture number 26, we will discuss the various component of the electroacoustics, that is first, and then we will try to relate the fundamentals of those principles or the parameters, electroacoustical parameters, and try to relate that with the architectural design of electroacoustics. Now, basically when I say about the electroacoustics, it is a kind of a sound reinforced system. The sound reinforced system is sometimes when a particular hall or particular area is too large, or sometimes I am going to produce some kind of a pre-recorded kind of a voice or music. We need to take help from the electromechanical systems, something like a loudspeaker, the microphones and all. In fact, today this NPTEL course or maybe this NPTEL course and all, everything is actually the game of a electroacoustical part. I have a speaker with, I mean the microphone with me, which is a collar microphone kind of a thing, and that is going to produce the sound to you through some electrical pulse, and then finally my sound is transmitted or captured by this particular this collar microphone, and it is sending some kind of electrical pulse, and finally when you reach into your the environment or your room or in your laptop or maybe in any kind of a computer device, or maybe it is your mobile, it is actually again translate that electrical pulse to a sound energies or so. So, this is the brief definition of the sound reinforcement or the sound electroacoustical systems. Now, what are the objective of these electroacoustical systems? There are 3 basic objectives of the electroacoustical systems. One is reinforce the sound. So, I have told you, if the size of this particular hall is very large, or there is a huge amount of audience, very high capacity of the volume, I have to take care. Sound probably it will be inadequate. I mean only the voice or any kind of a music which actually going to play in the stage, which is maybe very weak for the rear seat or some portion of the auditorium. So, you need to reinforce the sound by some kind of amplification. Then we have to provide some kind of the adequate loudness or maybe the adequate intelligibility, where we can actually hear the sound, actual sound, and the frequency of the sound without any kind of a distortion, and the loudness should be adequate. And sometimes we need many times we need the reproduce the sound which was recorded earlier, some music or maybe some kind of the voice or some kind of the performance which has been recorded earlier, and then that can be reproduced in some different locations. So, for that electroacoustical systems is required. Now, in this when we going to deal with some kind of electroacoustical systems, various component of it, we have some of the requirement. In requirement from that requirement point of view, the first requirement, the sound should travel to the audience of the in a large distance. That is the one of the basic fundamental requirement of electroacoustical systems. Otherwise, perhaps electroacoustical systems was not developed. And the second requirement is the adequacy of the sound level. Sound level has to maintain a kind of a adequate sound level in every part of the auditorium, not only in the front or maybe only in the back part, in the sides and also in the middle part of the auditorium. The uniform sound level, which is also a part of or a kind of a the adequacy point of view, we can judge the uniformity. So, there should not be a very high sound level in some point and very low sound level in some other point. So, it should have a flat kind of a character. The fourth one is very important. There should not be any distortion of the frequency of the sound. So, the sound frequency which comes out from any kind of a musical instrument, which comes out from some kind of someone's voice, should not be distorted. The same frequency, and as you know, the frequency is actually give you the character of the sound. So, that frequency should not be distorted. Suppose a tabla is playing over here, so that sound should be a bass or those kind of a frequency level, and maybe a guitar or maybe any other kind of instrument should not or maybe a piano should not distorted the voice after this amplification or the reinforcement. And finally, which always a architect deal or any kind of a engineer deal, which is a system durability and the total economy of the systems, that also we have to check from the various properties of the system component. So, next we will see the what are the basic component of the systems, I mean this electroacoustical systems. So, if I see in this particular slide, I have classified this system into three major parts. The initially it is a low level acoustical energy, which is provided by some kind of a performance or maybe some kind of a speech, has to taken into some kind of a input transducer, and then this particular thing, that particular acoustical energy has to go through some kind of a processing, which is called the signal processing, and then the high level acoustical energy has to be reach to the audience through some kind of the output transducer. And this input transducer or the low level acoustical energy can be taken through the microphones, which I have just now told you that this I have also a microphone over me. And then this particular microphone then went to the sound from the microphone, captured sound from the microphone went to the signal processing unit, which has basically two parts, one called the preamplifier or a mixer, and another one is called the power amplifier or the graphics equalizer. And finally, it goes to the loudspeaker, which is the output transducer, and the role of the loudspeaker is just translate the electrical signals to a sound signals once again. I have given this particular slide is some pictorial presentation. So, with that I can again restate that particular functions or the basic component: microphone, which convert the sound energy to the electrical energy. Then there are a lot of electronics arrangement, where the graphic equalizer, the power and the preamplifier has to make a common role, which is comes under some kind of the signal processing kind of thing, where they will actually separate out the frequencies HF and LF are the high frequency and the low frequency sound to the high frequency and the low frequency loudspeaker. And finally, the loudspeaker will convert the electrical energy to the airborne sound energies also. So, the first component, if I again go back, so first component is this particular the microphone. This microphone is the first component. So, let us discuss to one by one of this component and what are the various the requirement and what are the various types available. The microphone again what we have understand that is convert the sound energy or the sound wave to electrical impulse, and the types of if I say the types of sound sorry, the microphones are how I has divided into two type of that classification. In the first type of classification, I can say it is some kind of a within the shape and the use point of view. There are classification like handheld, shotgun, the ribbon or condenser or dynamic kind of a microphone. And if I went to work some kind of a directivity point of view, the how the microphone is behaving and how it is going to capture the sound and from which direction actually, then it has a omnidirectional, bidirectional or unidirectional. These three categories of the microphones are available, and that is the classification based on the directivity. Now, let us go one by one and see how these are actually look like, and the shape point of view and the use point of view, this handheld kind of microphone, which you must have seen in the hand of reporters in some kind of entertainment channels. They put in front of somebody's face and they give some kind of a bites that particular the journalist, and they use this particular type of handheld microphone kind of a thing. There are two types of handheld, one is with the cord or sometimes it is without cord, or the cordless kind of a microphones are also available. And the next one is the shotgun microphone, and that is extremely directional microphone, but that means it actually catches the sound from a very the distinct the direction point of view. So, if that particular direction has changed from some angle, it has a very poor kind of a output, it will show some kind of very poor output. It is very popular in the movie set and particularly in the news televisions or news studios, TV news studios, where a particular shotgun kind of a microphone is held in a particular direction or particular place, and the speech or maybe some kind of the dialogue can be captured. The next one is ribbon microphone, which actually used for the speeches, which actually used for the radio stations. This ribbon microphones are a bit older version, and in this modern days we have some better versions of this particular microphone, and it was used in kind of an announcement or those kind of a thing. If you have perhaps seen this kind of microphone in the telecasting, when they actually telecast the videos for the sports event like cricket or maybe football, in that particular booth where actually the commentators booth, where they actually sit and give the running commentary of any kind of a sports event, they use this kind of microphone. Radio stations also, for some kind of announcement in the railway stations or maybe any airport, they use this kind of microphone, ribbon microphone. Then the condenser microphone, again it is a old kind of version of the condenser microphone, which is a very wide range of the directivity, and this actually captures the vocals and the music of different area. If must have you have seen in a stage performance, musical performance like in a stage in a auditorium, this condenser microphone are each given to for the each the vocal or the musical instrument, and it will capture the sound from them. The last one is called the dynamic microphone, which is mostly used for the instrument like the guitars or drums. Again, this has a wonderful directivity, and this is a kind of a replacement of the condenser microphone to this dynamic microphone nowadays. And again I must say this dynamic microphone is that what we have seen in the very first, that is the handheld is one type of the dynamic microphone kind of a thing. So, those are the various classifications of the microphone from the virtue of the shape and the use. So, let us see what are the types available from the directivity. So, the first one is the omnidirectional, where I have plotted a diagram with a center point. I have placed that particular microphone, and this blue circular line gives the directivity it has. So, it is saying that it has almost the equal directivity, which is and it captures the sound from 360 degree. So, that is why it is called the omnidirectional kind of a microphone. And the bidirectional microphones are those which has a directivity only in the two opposite directions. So, one may be in the 0° direction and another one is the 180° direction. So, if you see the blue lines over here in this particular diagram, so from that you has, so the offset from the towards the 90° and the 270°, the capturing potential is little less. So, it is the property of this bidirectional kind of a microphone. The third one is the unidirectional type of microphone, where it is actually captured only from the one location, only from the front location. So, if it is in the 90° orientation or 180 or maybe in the 270° orientation, some sound comes from this side or maybe from back side or from this area, it does not have that much of effectivity. So, sometimes we use the unidirectional microphone just to avoid some kind of noise, maybe background noise or maybe noise from the sides. So, only when you focus a particular the source of the sound, and you know that particular source of the sound is located at a particular the typical point, then it is better to use the unidirectional kind of a microphone. Now, next talk about some kind of the what are the different properties of this microphone. The first property of the microphone is called the sensitivity of the microphone. How this microphone is sensitive, how much it is sensitive. So, it is really it actually translate in the definition wise that how much acoustical pressure is converted to this particular by this particular microphone, some kind of electrical impulse, because I have already told you what is the duty on the role of a microphone. It is captured the sound and then it translate the sound, that particular mechanical the vibration of the sound to the electrical impulse. So, the 1 kilohertz frequency of the sound at 94 dB SPL or 1 Pascal pressure, sound pressure, is the bottom or the decum level, and from that how much it is converting in millivolt unit in electrical signal is the sensitivity of a microphone. So, some microphone may provide much more millivolt and some microphone may not provide that much. From that point of view, I can give some kind of a stratification of the microphone sensitivity, but the input is 1 kilohertz with 94 dB sound, which is equivalent to almost 1 Pascal. So, I have given a pictorial diagram. So, suppose this is the audio wave or the sound wave, which is actually a mechanical wave. It is a the compression and refraction, it comes to this particular microphone. So, the input has to be 94 dB at 1 kilohertz and that equivalent to 1 Pascal. So, I have just calculated that this formula with 94 dB is the pressure I want to find out. So, it is 20 log, and then if I just rewrite this equation, then I find that this P, which is equivalent to 94 or which produce the 94 dB, is nothing but almost 1 Pascal. So, a 1 Pascal sound pressure is generated very near to the microphone, and you find out how much is the millivolt output from some kind of the electrical impulse recorder. You find out what is the millivolt output, and that will be the sensitivity of the microphone. After the microphone, the next stage what microphone does is that it has actually converted the signal, which is a sound or the mechanical signal, to a what is acoustical signal to a electrical impulse. Now, it will go to some signal processing, which is a secondary or the middle unit of the electroacoustical systems. So, it has to go through the preamplifier, which is also called as a mixer. So, its mix, first of all, it is going to mix some kind of frequencies, combine some kind of frequencies. Why? Because there may be lot of more than one output. Suppose there are some instruments, some vocals, and some other people may give some kind of a speech. So, in a stage or in a music recording room, there may be different musical instrument. So, you capture different the sound or the electrical impulse by virtue of different microphones. And then there is a very low level of signal amplification, very slightly low level of signal amplification it will do. Then in this particular process of the preamplifier, it will also minimize the noise. If there are some kind of a noise which is not wanted for the final delivery, so those noise has to be minimized by virtue of some kind of a screening and filtering in this particular preamplifier system. And this particular mixing, noise minimization and the amplification, slight amplification I must say, that will be given to the next part of the signal processing, which is called the power amplifier, or it is also known as sometimes graphic equalizer. It has majorly two jobs. This power amplifier, as the name suggests, it will amplify the power, increase the power of the signal, and then it will actually, which is one of the need for the electrical the electroacoustical systems, which is going to reinforce my sound. And the graphic equalizer controls the total audio, and different frequency bands and everything, they will give you kind of a overall control by virtue of some kind of you want to produce some kind of a music. Suppose you want to put the tabla sound little low and the guitar sound little high, and the voice of a particular singer is the furthermore high or low, whatever may be the situation, or a director, music director thinks. By virtue of that particular thinking, we can use some kind of the frequency band control and the equalization of this particular sound. So, that is one of the part, or one of the role, or one of the component that will actually perform in the power amplification. So, after this power amplification was going on, so there is a kind of a another ratio comes, or another parameter comes, which is called a signal to noise ratio, because there are some noise which I have shown here by virtue of some the red lines, which is a noise, but the desired sound is this part, that has to be taken into account. So, I have to actually take out this particular noise, and then the desired sound has to be filtered it. And for that, the signal to noise ratio has been taken as one of the basic parameter, where it has been right as from the power point of view, W signal by W noise, where the W's are the power of this particular signal and this noise, or sometimes it may be rewritten as a dB scale, when it is SNR is a signal to noise ratio in dB, which is 10 log of that, and it can be also rewritten as the amplitude functions also, when it will come under it is the amplitude square is the way it can be written. So, I can say that when the from the power point of view, SN ratio is 1. So, it is translate as a dB of SN ratio of 0, and when it is suppose 100 from power point of view, it goes like 20. So, after this the signal processings and all, we will let us see what are the loudspeaker. Loudspeaker is the final final part of this electroacoustical systems, where a particular electrical energy is now ready to transform, it is already amplified and it is ready to transform to sound and come back to the sound energy again and it now like to propagate, and it is called a driver. There is also loudspeakers are called final driver of the system. So, what are the use? There are 4 typical use. It is the oral communication, we use the loudspeaker, we use loudspeaker for the sound reinforcement, we use the loudspeaker for sound production, for some kind of a live performance, and some many a times we use this is for some kind of a reproduction, where a already recorded sound is reproduced by the loudspeaker. What are the types of the loudspeaker? Again, I have classified into 2 categories. From the frequency point of view, it is having the woofer, the mid range speaker, the tweeter and the full range device, and from the shape point of view, it can be classified as the horn, cabinet loudspeaker, or maybe the column loudspeaker. So, let us go one by one. The woofer is a kind of a loudspeaker which actually deliver the low frequency and bass sound, which is approximately 20 to 200 hertz, and they are further classified as the pre-woofer or maybe the subwoofer like that. And the mid-range speakers, as name suggests, it is taken care of the mid frequency level, which is 250, around 250 to 2000 hertz, and it is also take care of those particular mid frequencies and they deliver it properly. But this may not be very much effective for the low or high frequency, is also called squawk. And the final one is the tweeter, which is the actually design the high frequency sound for the high frequency sound, which goes with the 200 to 2000 kilohertz sound level also. And full range is for the audio full range from all the sound level from the mid to high and also the low frequency sound. So, these names, if you go back, if I go back to the names, that barking of dog is called woofer. So, it's that is why this low frequency barking of dog, that is why it is called woofer. The mid frequencies are squawkers, which is the squawk, you know that sound is kind of a mid frequency sound, and tweeter, that is birds tweetings and all, these are the high frequency of the sound, that is why they are called the tweeter kind of the loudspeaker. So, this is the from the shape point of view, these are the horn loudspeaker, which is very popular for the announcement or those kind of a thing. This is the cabinet loudspeaker, small and miniature versions cabinet, and there are 2-3 type of loudspeaker can be placed together, and there may be a column loudspeaker where there is a series of low or high frequency or a mixed kind of a things also may be placed in a series, in a vertical series. Now, similarly, like we deal with the microphones, the loudspeaker sensitivity is also one of the important things, where it can be defined as 1 watt 1 meter kind of a scenario, 1 watt 1 meter kind of a thing, which actually from 1 meter, if this power received from in this microphone is 1 watt 1 meter from the loudspeaker, and suppose this is producing 85 dB sound, then I can say this loudspeaker sensitivity is just simple 85 dB. So, how much I am receiving, that should be now fixed, that is 1 watt, and to receive 1 watt, what is the dB level of the loudspeaker at a distance 1 meter. And the next one is the directivity of the sound or the directivity of the loudspeaker, where loudspeaker actually provide kind of a directive sounds in a particular direction, and from the directivity point of view, it is a throw. Sometimes it is a long throw or sometimes it is a short kind of a throw. So, as you know that the long throws are go nearer to the loudspeaker, and the short throw goes to the nearer to the loudspeaker, and the long throw goes very farther away. So, from this point of view, it has been seen that it is depend upon the wavelength of the sound, and the wavelength of the sound when it is a bass or the low frequency sound, which is having a long wavelength, it has a short throw, something like this 50 hertz has a very short kind of a throw. And then again if I increase it little bit little bit higher throw, but it is the width narrower, a narrow width there. And the high frequency, if you go to the high frequency sound, it will be give you a more or shorter wavelength, and it will give you a more throw. Suppose if you go to the 500 or 1000, it will be narrower, but the throw length will be very high. So, something like this. So, this also has to taken into some mathematical model kind of a calculation with by virtue of some kind of a dimensionless number. The speaker circumference by the wavelength has they have computed as a dimensionless number, and they have said that suppose if I take the velocity of sound is 330 meter per second, and the wavelength for 50 hertz is 660 centimeter, and if you have a 10 centimeter the aperture or the dia of this particular speaker. So, if I compute this dimensional number pi d by lambda is 0.05, but for high frequency sound it is 1000 hertz to 33 centimeter. So, this particular dimensional number become 0.95, shows it has a higher amount of throw. So, now if I want to go with the 50 hertz, which is having a low amount of throw, and if I increase the number of speaker in a the horizontal or maybe a vertical distance. So, I use 3 such 10 plus 10 plus 10 30 centimeter. So, for each individual it has a dimensionless number is 0.05. Now, if I use 3, then the dia is increased by 30, and then if you recompute with the same wavelength, now it has become 0.14. So, this the purple color bulb will be the actual throw or the actual directivity of the this 3. So, the directivity is again computed by some factor called directivity factor. So, from the speaker in a very straightforward 0 degree line, suppose at this particular yellow point I got a the sound level as L average with a sound intensity of I average. But if I go some theta angle with a same radius R 1, so is red, I got the red point and I got the intensity as I theta and L theta, then by definition the directivity factor Q theta, theta means at particular angle theta is called I theta by I average at a particular radius R. So, this particular computation if you can do, now the L theta can be rewritten as this I format and the I can be written as that this way, the I reference into 10 into 10 to the power L theta by 10. So, if I use this I theta and I average and if I replace this by this the level sound pressure level or the sound intensity level, I get this as a final result. So, in terms of the SIL sound intensity level, Q theta can be rewritten as in this yellow box format. So, 10 to the power with this particular the L theta minus L average by 10. So, next is the directivity index. Directivity index is di of that particular theta is nothing but the 10 times logarithmic of this directivity factor Q theta. And if I open it this particular equation, it is nothing but the L theta minus L average. So, whatever may be the level of here and whatever may be the L average of here, the difference between them is the directivity index. So, let us go to a small mathematical understanding where suppose in this particular 0 degree line I got a 120 decibel, this is the L average, and if I move circular in a circular path without changing the radius from the loudspeaker at 30 degree I got 116. So, your directivity index is minus 4 dB, because 116 minus 120 is minus 4. Similarly, in L 60 degree it is suppose 110. So, it is minus 10 dB. So, what it can give me is that in this same radius if I move gradually the decibel level is slower down, and if I now go with this. So, at particular 30 degree it has a minus 4 and this is minus 10. So, I can say I can draw a concentric circle of minus 5, minus 10 dB something like that, and then I can say this equivalent sound level of this is nearly somewhere here, and equivalent sound level of this yellow which is in the 0 degree line is nearly here in the 60 degree line, because it is minus 10 from this particular and this is minus 4. And finally, if I draw this in a curve, I mean draw this particular points in the various circular segments in curve, I can actually draw a equal SPL line, and this is called the polar plot of the loudspeaker. So, there is this kind of polar plot can be drawn. So, in the left side this is a single polar plot, or this particular microphone the loudspeaker has this kind of a directivity, and this is the equal SPL contour. This is a maybe 2 or 3 microphones, or maybe a single microphone has this kind of a the directivity, little bit of complex directivity, where these are the polar plot of that particular loudspeaker. and this loudspeaker has, I have drawn blue and green. Suppose this blue and green are for maybe two different frequency. Suppose this is some high frequency and this is suppose some kind of a low frequency kind of a directivity and the equal SPL plots. So, this equal SPL plots comes from the directivity, which is a one of the significant property or the parameter of the loudspeaker, which we will again take into the next chapter, next discussion, lecture number 27 for further details. So, this lecture ends here. So, let us take some the homework, and this two homework I have designed is not a mathematical, it is just kind of a discussion or this just kind of a understanding. So, can you differentiate between the microphone and the loudspeaker sensitivity, and these are little, there is a little difference between them, the loudspeaker sensitivity and the microphone sensitivity. And you can another one is the how this directivity of the polar plots or these polar plots of a loudspeaker related, directivity and this polar plots how they are related, and what are the importance of this polar plots do you think for the electroacoustical design. So, that ends my lecture. These are the some of the books I have referred for this lecture, and next lecture in the lecture number 27 will go with some acoustical design principles. So, thank you for joining us, and let us move to the next lecture.